In this video, we're going to start exploring the basics of a branch of abstract algebra called Galois theory. Let me write that down over here. That's Galois theory. This is named after a French mathematician named Évariste Galois. Galois theory, in a nutshell, is a study of all of the cool stuff that we can understand about polynomials, field extensions, roots of polynomials, all of the wondrous things that we can understand about those creatures by thinking about automorphisms of field extensions. And that's what we're going to do in this video. I've put together a fairly basic lattice of field extensions of the rationals. So we got the rationals here, we got the rationals adjoining root 2 here, adjoining root 3 here, and then the rationals adjoining root 2 and root 3 here. And those, of course, are all extensions of degree 2, so I'll mark those accordingly in the diagram. The first question that we're going to ask and explore is, what automorphisms can we find of the field Q adjoin root 2 and root 3? So in other words, automorphisms phi from Q adjoin root 2 and root 3 to itself, such that phi of A is equal to A for every A in the rationals. So we're looking for all automorphisms of this extension field that fix every rational number. Okay, now that may seem like a really open-ended question. I mean, how in the world do you tame the set of all automorphisms of this big extension field, this one right here, that fix the rationals? By the way, any field that has the rationals as its prime field is going to have to fix the rationals. I don't want to dwell on this point too much, but if your field contains the rationals, then there's a theorem that phi of 1, if phi is an automorphism, phi of 1 has to equal 1. And then once you have that, you end up having every rational going to itself, because every rational is generated via field operations by 1. So having to fix the rationals, that's actually kind of tautological if we have an automorphism of the field Q adjoin root 2 and root 3. So anyway, how in the world do we get our head around all of the automorphisms that fix the rationals and that are from Q adjoin root 2, root 3 to itself? Well, one thing that we're going to use here is the fact that we know exactly what every element of Q adjoin root 2, root 3 looks like. Because we know by degree chasing that this extension field has degree 2 times 2 equals 4 over the rationals. So it's a vector space over the rationals of dimension 4. It can be written like this. It's the set of all A plus B root 2 plus C root 3 plus, and then what's the other basis element? Well, if we have root 2 and root 3, then we also have to have root 2 times root 3, which is root 6. So plus D root 6, such that A, B, C, and D are all rational. Okay, so that is a picture of what all elements of our field extension look like. A basis would be 1, root 2, root 3, root 6. And in fact, I'm going to go ahead and jot that down, because that's going to be the key fact that we use to get started in our analysis of automorphisms. Because we're going to think of this field extension not as just a random field, but as a vector space over the rationals with this basis, the basis 1, root 2, root 3, root 6. All right, so here's a fact. Every automorphism of Q adjoin root 2 and root 3 is a linear transformation of this vector space to itself. So I'll just say of Q adjoin root 2 and root 3 over the field of scalars Q. So in other words, I can understand what every automorphism does by understanding what it does to each basis element. Okay, and I want to illustrate why, just in case you're not totally fresh on your linear algebra here. Okay, so suppose we know what phi does. So let's say phi is an automorphism, does to 1, root 2, root 3, and root 6. So we have a definite image for each of those elements. Well then, any element of my field has to go to, that is under the automorphism, has to go to, well, I'm just going to write down phi of that same field element, and I'll unpack this in the next step. Okay, well that has to go to phi of A plus, and I'm just going to use properties of homomorphisms en masse here, phi of B, phi of root 2, plus phi of C, phi of root 3, plus phi of D, there we go, phi of root 6. Okay, and then I can further simplify that by saying, well, I know that we're assuming that all of our automorphisms fix every rational number. In fact, that's something that we know about automorphisms of a field extension of Q, is that they have to fix all the rationals. So phi of A has to be just A, because A is rational, B is rational, so this is just B, C is rational, so that's just C, and D is rational, so that's just D. Okay, so I have A plus B, not root 2, phi of root 2, there we go, plus C, phi of root 3, plus D, phi of root 6, whatever those things are. Okay, so what this means is that I can think of phi as being a linear transformation of this vector space over the rationals, because, well, what happens when I apply my transformation to this linear combo of 1, root 2, root 3, and root 6? Well, I end up with that same linear combination of the image of 1, root 2, root 3, and root 6 under the transformation. So that's a nice illustration of the principle that phi has to be a linear transformation. If I wanted to prove directly that phi would be a linear transformation, I would just prove that it satisfies all the properties that linear transformations have to have. So they got to preserve sums, and they got to preserve scalar multiples. I could prove both of those things pretty easily if I wanted to do it directly, but we're going to go ahead and forge onward here. Okay, so my point here is, so here's the point. To determine an automorphism of this field extension, I actually don't have to have that much information. I need to know what happens to the rationals, which I already know that they're all going to be fixed. I need to know what phi of square root of 2 is. I need to know what phi of square root of 3 is, and I need to know what phi of square root of 6 is. And actually, those are not going to be three totally separate, independent pieces of information, as we will see very shortly. So in other words, to know what phi is doing, know the values of phi of root 2, phi of root 3, and phi of root 6. But phi of root 6 is not really a separate piece of information. That's really just phi of root 2 times root 3, which is phi of root 2, which is already determined, times phi of root 3. So really I only have two decisions to make. I have to decide what this is, and I have to decide what this is. Okay, now that sounds like it might still be a lot of automorphisms, but really it's not. Because here's another thing that I know. If phi of root 2 is equal to alpha, then I also know that phi of 2 has to equal phi of root 2 times root 2, which is phi of root 2 times phi of root 2. And if I'm saying phi of root 2 is alpha, then that's alpha squared. And in the meantime, phi of 2, because 2 is rational, that has to be fixed. So that has to be 2. So alpha squared has to equal 2. In other words, root 2 has to get sent to something that qualifies as a square root of 2. Now that may seem boring. That may seem like I just have to send root 2 to itself. But there are two numbers whose square is equal to 2. Those are plus and minus root 2. So alpha has to be root 2 or negative root 2. And then the same story is true for phi of square root of 3. Phi of square root of 3 has to equal either root 3 or negative root 3. And then once I know what phi of square root of 2 is going to be, and what phi of square root of 3 is going to be, I know what phi of square root of 6 has to be, because it's got to be the product of whichever one of these I choose times whichever one of these I choose. All right, so here's what we're looking at. If we want to analyze the possible automorphisms of Q adjoin root 2, root 3 over Q, meaning that these automorphisms fix every rational number, well, here they are. I can create something kind of like a little Punnett square here. On this axis, I will put the image of square root of 2, and on this axis, I'll put the image of square root of 3. And then my choices for the image of root 2 are going to be plus and minus root 2 or negative root 2. And then for the image of root 3, I have to pick root 3 or negative root 3. Okay, so on the upper left, I'm going to send each of those square roots to itself, root 2 to itself, root 3 to itself. That's going to be the identity map. I'm just going to call that epsilon because I always associate the letter E with the identity. And epsilon, just so that we keep track of this as well, epsilon of root 6 is going to be root 6 because square root of 2 times square root of 3 is square root of 6. All right, now I also have the one on the upper right where I'm sending root 2 to negative root 2 but leaving root 3 alone. Let's call that phi sub 1. All right, phi sub 1 sends root 6 to negative root 2 times positive root 3. That's going to be negative root 6. All right, so that's phi sub 1. I'm going to call this one on the lower left phi sub 2. That's the one that sends root 2 itself, but root 3 to negative root 3. That one is also going to send root 6 to negative root 6. Because again, I'm just taking the product of the image of root 2 times the image of root 3. And then finally, I have this other one. Now, I could call that phi sub 3, but that seems kind of uncreative because it's actually obtainable from the other automorphisms in my picture here. Okay, because if I take square root of 2 to negative square root of 2, that's what phi 1 does, and then phi 2 takes root 3 to negative root 3, but leaves root 2 alone, I claim that this other automorphism here can be expressed as phi 1 composed with phi 2. And I'm reading right to left here, so that says do phi 1 first, and then do phi 2. You can actually verify that that automorphism sends root 2 to negative root 2 and root 3 to negative root 3, and therefore sends, now this is no way going to fit in the box, it sends square root of 6 to negative root 2 times negative root 3, which is, you guessed it, positive square root of 6. Okay, so I also have two automorphisms that send root 6 to itself, and two automorphisms that send root 6 to negative root 6. This is a group. It should look somewhat familiar to you. It's a group with 4 elements. This group is not a cyclic group on 4 elements because there is no one of these automorphisms that generates the entire group. And the reason that you know that is because every one of these automorphisms composed with itself gives the identity, even this one, because this one here is sending root 2 to negative root 2, root 3 to negative root 3. If you compose that with itself, it's going to send both of those back to the positive square roots. So this is an abelian group because every group of order 4 is abelian, but it's Z2 plus Z2. And it can be generated by this automorphism here, phi 1, and this automorphism here, phi 2. Okay, there's a total of 4 automorphisms and no more, which may be smaller than what you'd guessed at the beginning of this video. I mean, I would have guessed a much larger number if I hadn't known all of this already. Okay, so that is the group of automorphisms of Q adjoin root 2 and root 3 that fix all the rational numbers. Let's look at one more. What about the automorphisms of Q adjoin root 2 and root 3? Okay, so same field, but this time that fix Q adjoin root 2. So this time we're demanding that an automorphism fix not only the rationals, but also fixes the square root of 2, and every linear combination of rationals and root 2. Okay, this one's actually going to be quite a bit easier because we're fixing more stuff now. So let's see, let's come over here. All right, zoom. Okay, so this time we're going to look at what automorphisms of Q adjoin root 2 and root 3 fix Q adjoin root 2. I mean, I guess that one way we could approach this is, since every such automorphism has to fix the rationals, we could just come back down here to this table that we created and just ask ourselves which of these 4 automorphisms fix the square root of 2. Hint, it would be these 2. Okay, so that would give us a group of order 2, and that would be just Z mod 2. So there's a Z mod 2's worth of automorphisms of Q adjoin root 2 and root 3 that fix the square root of 2. But let's suppose that we hadn't already done that analysis. Then how might we think about this problem then? Well, one way that we could think about it, and I'm doing this, by the way, I mean, not that this is going to give us a different answer than what we've already gotten, but just because it can be kind of useful to think about this particular problem in a couple of different ways. So this time we're thinking of Q adjoin root 2, root 3 as a field extension of Q adjoin root 2 of degree 2, which means it is a vector space of dimension 2, and a basis for it would be, it's a set bracket there, 1 and the square root of 3. Okay, so in order to determine an automorphism that fixes Q adjoin root 2, we only have to determine what that automorphism does to 1 which is already determined it's going to go to 1, and square root of 3. Well, square root of 3 must go to either root 3 or negative root 3. Okay, so that's the only decision we get to make when deciding an automorphism of this field fixing Q adjoin root 2. So we really do only have those two automorphisms. We have the identity, which sends root 3 to root 3. Sorry, my pen's skipping like crazy now. And I think we were calling it phi sub 2 earlier, which sends root 3 to negative root 3. We already know what root 2 is doing because we're assuming that's fixed. So these are the two automorphisms. Now, one thing to notice here, looking back at the diagram, when we talked about automorphisms of this field fixing this one, we had 4 of them. And you'll notice that this is an extension of the rationals of total degree 4. If you look at this extension and this extension, 2 times 2 is 4. In the meantime, this was an extension of Q adjoin root 2 of degree 2, and we seem to have 2 automorphisms of this over this. That's not totally a coincidence. It's also not something that is true every time. There are some special conditions that have to be in place, and we will explore those.